Yeah. So S is a surface in R3, parameterized by, let's say, by phi 1. Okay. And then suppose that phi 2 is a reparameterization of S. So again, guys, I mean, on Tuesday, I gave you so many examples. So if you have a surface, the surface itself, it doesn't change, right? It's fixed. But the thing is, there are infinite ways to parameterize a surface, right? And I think I gave you a couple of examples. So about the reparameterizations of surfaces. So suppose that phi 2 is a reparameterization of S, of the surface S. So what we said is the surface S, all right? Then we said if this phi 2 is orientation preserving. So what's orientation preserving? Let me just write it down here. So first, if phi 2 is orientation preserving. So orientation preserving means that the normal vector, induced by phi 2 has the same direction as the normal vector induced by phi 1. So preserving, which means that the normal vectors induced by, so the normal vector, that's the remember guys, that's the capital TU cross capital TV. That's what I call the normal vector to the surface, right? So normal vectors induced by phi 1 and phi 2, they have same direction. All right. So if this is so if phi 2 reparameterization preserving, then your vector surface integral doesn't change. So then the vector surface integral of the vector field F along the surface S, so parameterized by phi 1, is equal to the vector surface integral of the vector field F along S parameterized by phi 2. Okay. And so we said, and then if this phi 2 is orientation reversing, okay, so orientation reversing means that normal vectors, they have induced by phi 1 and phi 2 have opposite direction, right? So normal vectors induced by phi 1 and phi 2 have opposite direction. Right? So this is again analog to the case of line integrals, the integrals along the paths. Then the vector surface integrals are going to be opposite. So this one here along S parameterized by phi 1 is equal to minus along S parameterized by phi 2. Right. So the conclusion, of course, is that this vector surface integral depends on the orientation. So we need to fix an orientation on the surface. When you compute, let's say, a vector surface integral, you need to fix an orientation. So the conclusion here. So we need to fix an orientation So the orientation here, in this case, in the case of surfaces, it's given again by this normal vector, right? And we said, so there are two possible orientations, right? Like, so you have a surface, you have this is your surface S. This is S. So there are two possible orientations in the sense that you'd have this, the normal vector would have this direction, right? So this is first the first possible orientation, right? This is your normal vector n, let's say, or n1, and the second possible, the other possible orientation is the opposite direction. So your normal vector would be like in this direction here. Okay. So here, so what I'm saying is there are two possible orientations, right? Again, given by the normal vector. Given by normal vector. Okay. So we need to fix an orientation when we compute or when we evaluate a vector surface integral. Okay. So here are some numerical examples as I promised. So this we discussed this on Tuesday. Now we didn't have any example, right? Numerical examples. So let me just give you an example and then an exercise. So here's an example and how to fix. So the question here. So how do we fix linear rotation on the surface? All right. Okay, so here's an example. Okay, let's say you have the vector field f. Let's say f of x, y, z is equal to, for example, minus y, x, and -1. So this is my vector field, right? Now I have, let's say, the surface S. S is the sphere, all right, of radius 1. So the sphere, x squared plus y squared plus z squared equals to 1, right? And now I'm gonna fix a new orientation here. So I'm gonna orient the sphere, with let's say an outward pointing normal. Outward pointing normal. Okay. So here I'm fixing the orientation, right? So I'm saying that the normal vector to my sphere, it must be an outward pointing normal, right? So so what I mean is, right, here's my space R3, here's my sphere, right? And then what I'm saying is the orientation is given by the outward pointing normal, so which means that this the normal vector must be outward. So it has this direction here. It's outward pointing normal, right? So this is outward pointing normal. So I need to make sure that the orientation induced by parametrization is actually it's given by outward pointing normal, right? So of course, if it goes inside, that will be inward pointing normal, right? So, here just to say, So just to remark that if it goes inside the sphere, so that will be an inward pointing normal. Okay. So on the sphere, I have two possible orientations, guys, right? The one outward and the other one is inward. And here in this problem, I'm fixing the orientation, and we need the orientation to be outward. Okay. Does this make sense to you guys? So you see what I mean by fixing the orientation here? So you have the sphere, which is your surface, and there are two possible orientations. So given by the normal, so either your normal vector is actually outward pointing or it's inward pointing, right? And here, so we are saying that our normal vector must be outward pointing normal. Now, if you parameterize the sphere, so I'm going to use just the usual parameterization for the sphere and see the direction of the normal vector, right? So the usual parameterization of the sphere. So the usual parameterization of the sphere so we had, phi of uv is equal to, I think it's cosine of u, sine of v, sine of u, sine of v, and then cosine of v. Okay, so this is because, this is usual parameterization because, it's if this is your x, if this is your y, and if this is your z, then if you do x squared plus y squared plus z squared, that will be equal to 1. Right? This is the usual parameterization. So the v, we said the u is between 0 and 2 pi. So u is between 0 and 2 pi, and v it must be between 0 and pi. Okay, so this is the standard, let's say the standard parameterization of the sphere, right? Now, let's see what would be the question here. What's the induced orientation of this parameterization? Okay, is it inward or is it outward? So what's the orientation induced by this parameterization? Okay, so the question, is it outward pointing or inward pointing, right? So again, the problem here in this, in the problem, we need to orient the sphere with an outward pointing normal, right? So we need an outward pointing normal, right? So let's see, what's the direction of the normal vector in this case? Well, we compute our normal vector. So, as usual, you first compute the derivative with respect to u. So it's just minus, sine of u, sine of v, cosine of u, sine of v, 0. So this is derivative of phi with respect to u. Derivative of phi with respect to v is just, cosine of u, cosine of v, sine of u. Derivative of sine of v would be cosine of v. And then cosine of v derivative is minus sine of v. Anyway, so now the normal vector, and so the normal vector is given, of course, by the tu cross tv, the cross product. So when you do the cross product, that will be minus sine square of v, cosine of u, minus sine square of v, sine of u, and then minus sine of v, cosine of v. Okay. So how do we check? How can we check the direction of this normal vector? How can we check if it's outward pointing or inward pointing? Okay, so all you have to do, guys, is just pick some point on the sphere. All right, so just pick and see what will be the direction of this normal vector. Okay, so let's pick a point on the sphere. Okay, to check the direction of this vector. Okay. Let's just pick a point. For example, I'm gonna pick. I mean, you can just pick a random point and see what will be the direction of this vector at that point. So let's pick. Let's say u is 0. Let's just pick some very simple point here. U is 0 and v is pi over 2. Okay, so what will be this point on the sphere? So phi of 0 pi over 2, that will be equal to, well, you just replace u by 0 and v by pi over 2. So it'll be 1, 0, and then let's see, cosine of pi over 2 is 0. So this is just the 0.100, right? This is just the 0.100. Okay. So again, here's my sphere. Let's say this is the x-axis, y and z. Here's my sphere, and all I'm saying is I have this point here. This is the point, the 0.100. That's my point. Okay. Now, what will be the normal vector at that point? So now, n or tu cross tv at the point 100. Okay, so again, at the point 100, u is 0 and v is pi over 2. So that's, let's see, where's my normal vector? It's here, right? So v is pi over 2, right? And u is 0. So here that will be equal to, so this component here would be equal to -1, right? Sine of 0 is 0. So this is 0. All right, and then cosine of pi over 2 will be 0. So the vector here would be the vector, -1, right? You get -1 here, you get 0 here, and 0 here. Okay, because again, your u is 0 and your v is pi over 2. So you get the vector -1, 0, 0, right? Again, because my u is 0 and v is pi over 2. Okay, so what we are saying, guys, is that at this point 100, you're gonna get the vector -100. Now, how do we? So here's my point. That's my initial point. It's the point 100, and you're gonna draw the vector -100 starting from the point 100. So -100. So it's gonna be in this direction, right? If your initial point is 100, then this would be the vector -100, right? So that's my normal vector n at the point 100. It's -1, so it goes in the opposite direction, right? So the question is this inward pointing or outward pointing? Well, it goes inside the sphere, right? So this vector -100 is inward pointing, okay? So this is inward pointing normal, okay? So that's not the orientation required in this problem. So in this problem, we are asking for the orientation in this problem. We orient the sphere with an we need to orient the sphere with an outward pointing normal, not inward pointing normal, right? So that's not the right orientation, right? So this is not. So that's not the orientation required in the problem. Okay. Does this make sense to you guys? I mean, you see why this is not the right orientation, right? So it's because it's inward pointing, right? And in the problem, we need to orient the sphere with outward. So what can we do in this case? So if you want to reverse the orientation, guys, that is a very simple trick. So here, this trick, a very simple way to reverse the orientation is so we have these coordinates parameters u and v, right? And you want to reverse the orientation, right? So the idea here, the simplest way actually to reverse the orientation is to in some sense switch the order of u and v. So is to, let's say, to change or switch the order of u and v. Okay, so what we're going to do, we're going to define new parameters. Okay, let's start with s. So s, let's say, is equal to v, and t is equal to u. Okay, and so now, so I have a new parameterization, let's say phi 2. So this phi 2 of s and t. You see, guys, here what I mean by I change the order of the parameters. You know, this is s and t, but s now s is equal to v and t is equal to u, right? So in some sense, now I start with v and then I have u, right? In the previous parameterization, we started with, we start with the u first and then v. Right now, to reverse the orientation, what we can do is just to start with v first, which is s, right, and then u. Okay. So here, so we start with v first, and then okay, so now, so what will be this parameterization? Well, as I said, since s is equal to v, this t is equal to u, so it's going to be just cosine of t. So again, I'm using this parameterization here. Here's my phi of uv, right? And all I'm saying is that now s is equal to v. So the s is equal to v and t is equal to u. So now cosine of u becomes, for example, cosine of t, right? Sine of v becomes sine of s, etc., right? So so we're gonna get cosine of t, sine of s, and then sine of t, sine of s, and then cosine of s. Right? V is between 0 and pi, so then s is equal to v, so s is between 0 and pi, and then t I mean, t is equal to u. U is supposed to be between 0 and 2 pi. So then t is between 0 and 2 pi. All right. Now, if you compute the normal vector induced by this parameterization, right? So you're going to have now, let's say TS, right? It's just cosine of derivative with respect to s, so the cosine of t, cosine of s, sine of t, cosine of s minus sine of s. All right, and then derivative t lower index lowercase t, the derivative with respect to t, that will be minus sine of t, sine of s, cosine of t, sine of s, and then 0. And now if you do ts cross t lowercase t, so that will be equal to actually sine square of s, cosine of t, now sine square of s, sine of t, and then cosine of s, sine of s. All right. So now let's see if this is if this normal vector is inward pointing or outward pointing. Okay, so again, I'm gonna pick a point. So let's just pick the same point. Let's say S. So again, pick a point. I'm gonna just pick the same point. So let's say S is pi over 2 and t is 0. Okay. So again, so then phi 2 of this point. So pi 2 pi over 2 0. So that would be the point. So here's my here's my phi 2, right? So we're saying t is 0, and s is pi over 2. So that will be 1, sine of 0 is 0, and then let's see, and then cosine of pi over 2 is 0. So that will be again the same point, the point 1, 0, 0. So this is again the point 1, 0, 0. All right. So again, I'm gonna have this point here. Right, this is this point here, the point 1, 0, 0. All right. Now, what's the normal vector at the point 1, 0, 0? So I'm going to have my TS cross T cross product with t lowercase t at the point 1, 0, 0. So at the point 1, 0, 0, again, s is, so here, s is pi over 2. And t is 0, right? So here's my normal vector. S is pi over 2, t is 0, so that will be equal to, so here is going to be 1, here sine of 0 is 0, and then sine of pi over 2, cosine of pi over 2 is 0. All right. Sorry, this is here. This is yes, so 0 here. All right. So you see the normal vector at the point 1, 0, 0 is the vector 1, 0, 0. So if you draw now the vector 1, 0, 0 starting from the point 1, 0, 0, so here is my vector. So here's my vector. Again, this is supposed to be x-axis here, y, and here's z. So that's the vector 1, 0, 0. Okay. And in this case, it will be outward pointing normal. So this is outward pointing normal. And that's exactly what we need, right? We need an outward pointing normal. So you see, guys, when you switch the order of the parameters, so then you can reverse your orientation, okay? So in the test or in the homework or in the final, I mean, you have to, if you have to, orient your surface, all you have to do is to find the parameterization, then check if if the induced orientation is the right one. If it's not, then all you have to do is just to change the order of the parameters. Okay. Okay, so now I got the right. So this is the right, the required orientation, right? This is, so that's the right orientation. Okay. And now I can evaluate we can evaluate our vector surface integral. Okay, so that will be, the double integral f along this sphere. All right, so we are using this so you're using this parameterization with this phi 2, right? So then we are using these parameters s and t. So f along the sphere would be equal to, so this is double integral, double integral of your minus, so again, f of x, y, z, we said is equal to, I think it was minus y, x, -1, right? So y would be equal to, so if you use this parameterization phi 2, so y is the sine of t, sine of s. So that's minus sine of t, sine of s, right? So this is minus sine of t, sine of s. X would be cosine of t, cosine of s, sorry, sine of s, sine of s, and then it's -1. Scalar product, of course, this is a scalar product with the normal vector, with the right, with the outward pointing direction, right? So that will be equal to, this is sine square of s, cosine of t, sine square of s, sine of t, and then cosine of s, sine of s, right? So this is my vector field f along the surface s. This is my ts cross t lowercase t, and then of course the variables here, ds dt, right? So s is between 0 and pi, and then t is between 0 and 2 pi, right? Okay, and then just you do the scalar product, etc., etc. So I think here you're gonna have cancellation. It's gonna be just so this is gonna be just equal to, this is 0 2 pi, 0 pi. So the first two components actually they're gonna cancel out, and we're gonna end up with just minus cosine of s, sine of s, ds dt. So that would be 2 pi. Derivative of, let's say, cosine is minus sine, so that's cosine square of s over 2. All right, between 0 and pi. All right, and then cosine of pi is -1, but that's -1 square, minus cosine of 0, it's 1. So that's just my 1 minus 1 would be 0. So the answer here actually is going to be 0, I think. Right. Anyway, so the computations here that are not really important. What's really important for you guys is to fix the right orientation for your vector surface integral. Okay. Any question about this example, guys? No questions. All right. So there's an exercise, a similar problem. So again, the main thing here is to find the right orientation, right, for your surface. So here's an exercise. Similar problem. All right. So let's say you have this vector field F, which is let's say 2x, 2y, and z squared. All right, and S, the surface S, is a portion of a cone. Portion of the cone, z squared equals to x squared plus y squared, with z between -2 and +1. So z is between -2 and +1. All right, so in other words, so here's your cone. But we're gonna just take the portion between -2 and +1. So it's like here is +1, and then somewhere here in the bottom, you're gonna have here's your -2. Okay. So that's your cone. That's your surface. And the orientation here. So this cone, or this portion of the cone, is oriented with outward. Let me just use the red here for outward. So with outward pointing normal. Outward pointing normal. So what does it mean? Outward pointing normal. So here's my cone. So the outward pointing normal should be, so the direction would be like this here, right? It's outward. So it goes like outside the cone, not inside. Okay. I'm gonna just probably remind you the parameterization of the cone in this case, and then all you have to do, guys, is to check the direction of your normal vector. So you have to check if it's outward or inward. Okay, so the standard, the standard parameterization of the cone would be so that will be phi, let's say phi1 of uv. So it's u cosine of v, u sine of v, and then u. That's because, if this is your x, if this is your y, if this is your z, so if you do x squared plus y squared, that will be z squared, right? And then the domain, of course, the z, that's u. Z must be between -2 and 1. So your u must be between -2 and 1, and v is just the angle. So it's because it's the whole cone here. So the angle is just between 0 and 2 pi. All right. So my question for you guys is, what's the direction of the induced orientation of this parameterization? So the question here. So is the induced orientation outward or inward? Okay, pointing. Okay, and if it's inward, then you need to fix it, right? So because again, what's required here, the orientation required in this problem, you need the outward pointing normal, right? So if it's inward, so then you have to fix it. So you need to change it to outward. All right. So that's what I mean by fix it. Change it to outward. So all you have to do, guys, I mean, this is again similar to the previous problem. First, of course, you have to compute your normal vector, which is the TU cross TV, and then pick a point and pick a point and then check if it's outward or inward pointing. If it's inward pointing, then all you have to do is just to switch, change the order of the parameters, as I did in the previous example. So let's say you have 3-4 minutes, guys, to think about this. So after this, after this exercise, guys, so we're gonna move to the Stokes and Gauss divergence theorems. So that will be section 8.2, 8.4. So hopefully today I'm gonna cover Stokes theorem, because I'm gonna give you a lot of examples, of course, and I'm gonna try to explain the power actually of this Stokes theorem. And then probably on next Tuesday, I'm going to cover Gauss, and I guess probably I would have time to start to talk about the last, last sections in the syllabus, and that will be the differential forms. So I'm going to talk probably a little bit about differential forms, and I'm going to talk about one of the applications of this, this whole parameterized surfaces is how to compute the curvature of a surface. Remember, in Calc-Phi, guys, you computed the curvature of a path or a curve, right? And so the surfaces also have a curvature, right? So what we are doing, guys, now it's a sort of, I would say, introduction to differential geometry. Okay, this is a differential geometry is one field in the, in mathematics. It's very, very connected to physics. Differential geometry is very connected to physics. For example, to theory of general relativity. Space-time, string theory, all that stuff is very connected, related to differential geometry. And that's exactly what we are doing now. We are studying surfaces, or in other words, we are studying the geometry of surfaces, the parameterization of surfaces, orientation of surfaces. That's like the basics of, just geometry of surfaces. Anyway, and actually differential geometry is my field. That's what I do. I mean, my research is focused on differential geometry.
I've got vector 0, -1, 1.
0, minus?
Minus 1 and 1. I picked up the point u equals to 1 and v equals to pi over 2.
Okay, so 0, negative, at which point? At what point? Do you think it's inward or outward?
Oh, I didn't check the point yet. Just
okay.
a sec.
Yeah, yeah. So you have to check the direction if it's outward pointing or inward pointing. I would say the simplest point would be the 0.10. If u is 1 and v is 0, for example, that would be very simple, I guess, to check. I mean, you just pick any random point, but you need to see if the normal goes like inside or outside your cone.
Oh yeah, I got it. So it will be inward point. Yeah.
Inward, yes, absolutely. It's going to be inward. So you have to change your orientation. So and again, the idea to change the orientation is just to switch the order of parameters. So you can define new variable parameters s and t. Let's say s is equal to v, t is equal to u, but you're gonna start with s, which is equal to v. But yeah, but you're right. Yeah. So the orientation here and used by this parameterization phi1 is going to be inward pointing. Absolutely. Very good. All right. So let me. Okay. So I guess you don't have to compute the vector. I mean, the goal here is to fix this orientation, right? I mean, we know how to compute, well, yeah, we know how to compute this the vector surface integral in general. So I guess again, the main thing here is just to fix the orientation. So yeah, as visible as said, so it's going to be inward in this case. So let me just quickly do the computations here. So if you do derivative with respect to u, I think it will be cosine of v, sine of v, and 1. Do the derivative with respect to v, that would be minus u sine of v, u plus u cosine of v, and 0. And then if you do normal vector, so the cross product, if you do the cross product, so this is my normal vector, let's say n1, just tu cross tv, so that will be equal to the sum minus u cosine of v, I guess, minus u sine of v, and plus 1 cosine square minus, so that will be u. Okay, so that's my normal vector. Now I'm gonna pick a point. So again, here's my cone, right? Okay, and I'm gonna just pick a point. Let's pick a point 1, 0. That would be the simplest point, I guess. So pick a random point. So let's say u is equal to 1 and v equals to 0. Okay, so that would be the point of phi1 of 1, 0. So that will be equal to, let's see, so that will be the point. So u cosine of v, cosine of 0 is 1, of course, that will be 1. U sine of v is 0, 0, so that will be 0, and then you're gonna have u, which is 1. So that's the point 1, 0, 1. So 1, 0, 1 would be somewhere, let's say, this is x here, so this is y, this is z. So the point 1, 0, 1, it will be somewhere here, I guess, right? It's in the direction of the x-axis with the height as z equals to 1. Anyway, so that's my point. This is my point 1, 0, 1. Okay, and now I'm gonna compute the normal vector at that point. So what's my normal vector n, which is tu cross tv at the point 1, 0, 1. At the point 1, 0, 1. So that will be the vector. Let's see. So u is 1, v is 0. So that will be negative 1, and then 0, and then positive 1. Right. So it's negative 1, 0, and positive 1. All right. So this vector. So you have to draw this vector starting from the point 1, 0, 1. Right. So here's my point 1, 0, 1. So I have to go like negative 1 in the direction of the x-axis, and then 0 in the direction of y, and then 1 in the direction of z, right? So that would be probably this this vector here. All right, so anyway, it goes -1 in the direction of x, so it goes in the opposite direction of the x-axis, right? So it's actually, this is the vector, so this is, let's say this is the vector -1, 0, +1. So it's inward, right? Because it goes like sort of inside the cone, not outside the cone, right? So this is inward pointing normal. Okay, goes inside the cone, and so to change the orientation, all you have to do, guys, so we have to change the orientation. So we have to change okay, so we're gonna just apply our trick. So all you have to do is to define new variables or new parameters. Define, let's say, s and t, but s would be the first parameter. S would be equal to v. That was the second. V was the second parameter in phi1, right? Now I'm gonna start with the v first. So my first parameter is v. The second parameter is u, right? So now I have this phi2 of s and t. So you see again here, your s, the first parameter, now it's actually v, and the second parameter now it's u, okay, and etc. So then you can check, I mean, that's just the computations here. So we can check claim, as I did in the previous example. So I claim that the orientation induced by phi2 is outward. Is outward pointing. Okay. I mean, you may ask why, when we change the order of the variables, that would change the orientation of your surface. The reason is very simple, guys, is because, so the idea is that, so here you have u and v, right? This is u, this is v, and here it's, this is s and let's say t. Okay, so if you, so you have these two parameters, u and v, right? This is, you have this phi of u and v, okay? So because you start with u here, it means that in some sense, the orientation here in the domain, in R2, so you go from u to v. So the orientation is this one here in the domain of phi, or phi1, okay? Now, in phi2, with the s and t, of course, you start with s, you go to t, okay? But now the thing is, this s is now is v, and this t is u. So in some sense, now you're going from v to u. Okay, so you're reversing the orientation now when you switch the order of the parameters. Okay. Anyway, so that's basically the idea. Any question, guys? All right, so no questions. So I think we are done with this, the surface integrals. I think we covered a lot of things in this surface integrals. Actually, I didn't define the orientation of a surface. I mean, of course, it's given by this normal vector, yeah, well, I think we covered a lot in this section, actually. All right, so now it's time to move to the next sections, which are Stokes and Gauss divergence here. So let's probably move to the new page here. So this is actually section 8.2 and 8.4. So this is Stokes and Gauss divergence theorems. Okay. First, we're going to start with the Stokes theorem. Remember, guys, when we discussed Green's theorem, I said the Stokes theorem would be a generalization of Green's theorem. So first, what I'm going to do, I'm going to remind you Green's theorem, so you can see why Stokes is sort of a generalization of the Gauss theorem, right? Let me just remind you Green's theorem, okay? So Green's theorem, we discussed Green's theorem in section. Which section was that? I forgot, sorry. Let me find it. Well, it's not really important, but I'm just, oh, I don't know. So, Green's theorem. This is supposed to be a capital G, all right? Green's theorem. So what does it say, Green's theorem? Remember, we have this, some region or a surface in R2. So we have this D, closed, bounded region in the plane, right? It's in R2, okay? And with the boundary, of course, we had some conditions on the boundary. The boundary must be like a simple closed, whose boundary, the boundary of D, the boundary is actually finally is given by finally many simple closed curves, right? So this is just a simple closed curves. And we had to fix, an orientation of this boundary. Remember, this curve, this boundary are oriented so that the D, the region D, would be on the left as one traverse the boundary, right? So the D, so the C oriented so that D is on the left, right? As one traverses the boundary. Anyway, so we have the vector field F in R2. So F Y, it's in R2. So we have like it had two components, two functions, M and N, right? It's in R2. So you see everything here is in R2, okay? And so the Green's theorem says the following. So it says that this, so it relates the vector line integral. So the integral of this vector field along the boundary to some double integral over this region D. So the vector line integral of F along the boundary is actually equal to the double integral over D of this region D. This is partial N, partial X, partial M, partial Y, dx dy. Anyway, again, so the idea between the Gauss theorem is that you have this relation between one-dimensional integral along the boundary with a two-dimensional integral over your region D. But everything here is R2, right? And we said we have this vector reformulation of the Green's theorem. So in R3, so if you consider this vector field as a vector field in R3, so this is vector reformulation in R3. Okay, so now we are in R3, right? In this space. So your vector field F would be, you can write F as well, it's supposed to be now, we're supposed to have 3 variables now, right? So this is your f can be written as, so you have this function of xy, there's no z, there's this function n of xy again, and then the third component is just 0, okay? Because, you know, the f is supposed to have just 2 components, so the third component would be just 0. Right, and then we introduced the curl of f. So we said the curl of f. That's the, remember. So we said the curl of f. It's defined, or it's given by the cross product of the del operator with f. Okay, that's what we call the curl of f. The del operator, guys, here, the symbol here. This is the del operator. So this is equal to, so this is just a partial derivative. So it's partial x, partial y, and partial z. Okay. Again, this letter here, this is a Greek letter. This is a nabla, a capital nabla. So this is a capital nabla. Oops. This is nabla. Okay, it's a Greek letter. It's called nabla, and that's why I call it del operator. So this is what I call the del operator. Anyway, so that's just the definition of the curl of f. It's just a nabla cross f. All right, and so if you do the curl of this particular f, this one here, okay, then so if f is equal to m of xy, n of xy, and 0, all right, then curl of f, if you compute this cross product, then it will be just 0, 0, and then partial n, partial x, minus partial m, partial y. And this is exactly the term that appears in the Green's theorem, right? This is, so this is what we have in Green's theorem, right? This difference between the partial n, partial x, and partial m, partial y. Anyway, so, and that's in the k component, right? This is, so in other words, this is equal to, you know, partial n, partial x, minus partial m, partial y, times the vector k, right? The vector k is the vector 0, 0, 1. Remember, guys, of course, so so k, that's the vector 0, 0, 1, right? That's the third component of your vector. So another way to write this Green's theorem is, so Green's theorem becomes, so again, we have this vector line integral. So this the line integral of this vector field f along the boundary of your region D. This would be sorry, this would be equal to this double integral of the curl of f, right? Because we said that's exactly what we have in Green's theorem, right? Curl of f, of course, scalar product with the vector k, right? That gives you exactly this this component. All right, dA. dA, of course, that's just the area element. Okay, so the question, guys, what about the curl of f with f, you know, vector field f, given by you know, vector field f in the space? So this vector field f in Green's theorem, it's just a vector field in the plane, right? It has only 2 components. The third component is 0. So the question is, what about the vector field in the space? So the question is, so what about f in R3? So in other words, In other words, so if my f, sorry, in other words, f is equal to, let's say, a function m of xyz, a function n of xyz, and then a function L of xyz. Okay. Yeah. So in that sense, Stokes' theorem is a generalization of Green's theorem. So the idea is that, as I said, so this Stokes theorem. So what you need to keep in mind, guys, after the end of the semester, if someone asks you what's the Stokes theorem, so Stokes theorem is a generalization of Green's theorem, and it relates. So Stokes theorem is a generalization of Green's theorem. And so we're gonna have the same thing, Green's theorem. So it relates, the surface integral of the curl of vector field f over surface to a line integral, or this vector line integral of f along the boundary of the surface in Rp. So it relates the surface integral. So that's the double integral. That's the integral over the surface S. So the surface integral of the curl of f over a surface. Okay, so here it was over this domain D in the plane. Now it's over a surface in Rp. So now it's a surface in Rp. Okay. Again, in the Green's theorem, the domain D was in R2. So over a surface in Rp to a line integral, or to a vector, to the line integral of f along the boundary, to the line integral of f of the vector field along the boundary of this surface in Rp. Okay. So curl of f is related, the surface integral of the curl of f is related to this line integral of f along the boundary. So before I state the Stokes theorem and before the examples, etc., we need to fix orientation, right? Because remember, in Green's theorem, in Green's theorem, we said we need to orient. Remember here, this curve or this boundary here, the boundary of D must be oriented so that the surface is on the left, right? So we need to fix some orientation here, like in Green's theorem. So first, I'm gonna fix the orientation of our surface. So first thing, we need to fix some orientation here. First thing. So before the theorem, so we need to fix some orientation here. Okay. So how does it work? How does this orientation work in the Stokes theorem? So because now we are in this space, we are in Rp, right? So so here's the how it works. So the orientation. So first we start with this surface S. So we have some surface S in the. So S is some surface, in the space in Rp. So let's say it's some surface, bounded surface. Let's say it's also smooth. Okay, and it has some orientation, right? We know how to orient surfaces, right? Again, surfaces, they have two possible orientations. There's the inward pointing and the outward pointing, right? So let's say it's oriented. So we know we fix the orientation on S, oriented. Okay, in ortho. Okay, so the orientation here on S is fixed. So the normal vector direction of the normal vector is fixed. Is fixed, right? So you know if it's inward or outward pointing. Anyway, so now how we gonna orient the boundaries? So let's say now we have this curve, which is a simple closed curve lying on in S. So let's say the C. So let's see. Okay, it's some simple, closed curve line in S. So for example, the boundary of S or something, okay? So we need to orient this this boundary C, okay, or this curve C. But so the orientation of this curve C must be consistent with the orientation of S. Okay, so we say that we say that C, this curve C, is oriented constantly with S. Okay. With S, or because again the surface is already oriented, right? We fix this direction of the normal vector. So the orientation of this curve C is going to be consistent with the orientation of S if. So what we need to do, guys, we're going to use the right hand rule. Okay, so we use. So we use the right hand rule. So in some sense, the fingers of your hand, they curl in the direction of the orientation. So we use the right hand rule. All right. So, the fingers of your hand, your right hand, they will curl in the direction of the orientation. Okay, so your thumb of your right hand points along the normal vector N, okay, of the orientation here. Okay, so the thumb of your right hand points along your normal vector. That's the normal vector to the surface, right? Okay. The index finger points along the orientation of the curve. The index finger points along the orientation of the curve. Orientation of the curve of C. Okay, and then the middle finger will point inside the middle, inside the portion of the surface bounded by C. So the middle finger points inside the portion of S bounded by C. Portion of S bounded by C. Bounded by C. Okay. in other words, so let me graph here to give you an idea here. So let's say you have this. Let's say this is my surface S. Okay. I don't know if I can use probably. Anyway, so this is my surface S. Okay, and my surface S is oriented with this, let's say, upward normal vector. Okay, this is my N. Okay, it's upward pointing, for example. All right. Now, let's say you have some curve lying in S. So closed. Okay, so here's my C. Okay. So this is my normal vector, right? This is my normal vector. So what you need to do, guys, is to use this, as I said, the right-hand rule, right? So the thumb points along the normal vector, right? Along this one here. Okay. Now your index finger would point in the along the orientation of C. So like in this case, we'd have, so let's say the orientation of C is this one here. Right, this is the orientation of C. Okay, and then your middle finger will point inside the portion of S bounded by C. So the third, so the middle finger would point inside here. Inside this, the portion of S bounded by C. Okay, and so you can imagine you have your, you use your right hand, right, the thumb along the normal, the index along the orientation of the curve, and the middle finger would point inside the portion of S bounded by C. All right. Well, I don't know. I mean, I can. Okay, here's another example. I mean, I can. Well, that's probably hard really to explain, but I mean, here's another example. Let's say here's my surface S. Okay, let's say this is my surface S, and let's say my surface S is. Let's say I have this curves. This is my curve C. Okay, this is my C. Okay, and let's say my surface S is oriented with an inward normal vector. So let's say this is N. Okay, so you take your right hand, your thumb points in along the normal normal vector. So you curl your fingers, right, of your right hand. So thumb is the normal vector. The index finger would point along the orientation of C, and then the middle finger would orient points inside the portion of S bounded by C. So like in here, in this case, well, I guess it's hard to explain, but well, it's not really hard, but
can you show how it will look?
yeah. So like here in this case, the orientation of the curve would be like in this direction, and because your middle finger points inside, so the middle finger would go inside. So it's like it goes, inside. So like here, right? It's inside. That will be the middle, middle finger. All right. I don't know if I can probably stop sharing the screen, and we can probably see my let's see, hard to just what I'm gonna do. Well, this is your middle finger. Actually, this is supposed to be different vector here. Okay, so you can imagine in this case, you'd have yeah. So in these two cases, the orientation of C in this case would be consistent with the orientation of S. So like here, so this orientation, this one here, this orientation here would be consistent with the orientation of S. because the thing is, if I stop sharing the screen, I'm gonna lose everything. I'm gonna lose everything in the board. Anyway, just take your right hand, guys. Curl, you have to, the fingers, they must curl in the direction of the orientation, right? Thumb points in the direction of along the normal vector. The index points along the orientation of C, and then the third, the middle finger, which points inside inside the portion of S bounded by C. Like, I don't know, if I stop sharing the screen, I'm scared that I'm gonna lose everything in the board.
Yeah, but we still see you. I mean,
oh, you still see me?
yeah.
Oh, okay. So do you see my, like, in this case, you see my fingers? Do you see my fingers? I'm not sure because I don't see my.
Yeah, we do see.
Oh, okay. So you see, this is my right hand, right? So my fingers, they curl in the direction of the orientation. So you see, there's this. So my thumb points in the direction of the normal vector, and my index finger points along the orientation of C, right? It goes like this, right? And the middle finger, it's inside it points inside the portion of S bounded by the C, right? So it's like this, right? Makes sense to you guys? Thumb points along the N, the index points along the orientation of C, right? And the middle points inside the surface S, inside the portion of S bounded by C. All right. So like if your normal vector was the other direction, right? So then you have to orient the C in the other direction, because you see now my index finger would go to the opposite direction, right? If my normal vector, my thumb points on the other opposite direction, then my index would is going to point along the opposite direction, right? Anyway, doesn't make sense to you guys? I don't know if it's.
I think so, but I'm not sure.
Okay, like like in the first example, you see, like in the first example, so you see my thumb, it points in the direction of the normal vector, right? And so the index, points along the orientation of C. So like this is, all right. So this is like, here's my thumb, and this is supposed to be my index finger, and then the inside, that would be the middle finger. The inside, but that's the middle finger. Right, that's the middle finger. So in this first example, you see, this is my thumb here. That's my normal vector. This is, my index is points along the curve, the orientation of the curve C. So when you curl your fingers, okay, you get exactly the orientation, right? It's given by these three vectors, right? You have the normal, you have the orientation of C, and then the middle finger, that would be the vector which points inside the portion of S bounded by C.
Yeah, okay, I think I got it.
All right. But you have to use your right hand. Okay, that's the right hand rule. Okay, so thumb, that's the normal vector. The index, that's the orientation of the curve, and the middle finger, that's supposed to points on the inside inside the portion of S bounded by the curve C. All right. Okay, so that's for the orientation. That's what I call consistent orientation, consistent with the the orientation of the curve consistent with the orientation of the surface. So what does Stokes' theorem say? Well, so here's Stokes' theorem. So we have this start with some surface in the space, of course, right? So let S be a bounded smooth surface. In R3 in the space, right? Oriented. Okay, so you have some orientation. Oriented, right? And then suppose that the boundary. So as in the Green's theorem, you suppose that the boundary of S so is given by finitely many simple closed curves. Okay, it consists of finitely many simple closed curves. And as I said, sorry, the orientation of the curve must be fixed. So it's the curves, the boundary oriented. So the orientation of the boundary must be consistent with the orientation of the surface, as I explained in the before, right? So oriented constantly, so constantly here with S. Okay. Now take some vector field whose domain includes S, of course. So let F be a vector field. Vector field, as I said, domain of F includes S, all right? Because we want to integrate this F along S. Anyway, so what Stokes' theorem says is that so the double integral over the surface S of the curl of F is equal to the line integral along the boundary of S of the vector field F. Okay. So again, the idea is you have this double integral, which is a double integral of the curl of F. It's actually related to the line integral of the vector field itself along the boundary. Okay. So let me give you an example, guys, and I'm going to show you why this is kind of a very powerful theorem. Okay, so an example. Oops. Example. So in this example, what we're going to do, we're going to verify Stokes' theorem. So we're going to verify Stokes' theorem. Oh yeah, by the way, guys, I don't think when I say verify, like in the homework, there are some problems like in the homework number 4 where we have to verify Green's theorem. So when I say like verify Green's theorem or verify Stokes' theorem, so we have to compare the both sides of the equation, right? So you have to compute, you have to evaluate both sides and compare the answers, right? So of course they must be equal by the theorem. But that's what I mean by verify. I think probably David, you forgot to. I mean, when you when you verify Green's theorem, you just evaluate one side of the theorem, right? So guys, you have to evaluate both sides of the equation. Anyway, so let's say in this example, so we're gonna verify Stokes' theorem. So the surface S, let's say S is the paraboloid So in homework number 6, guys, the last problem, you have to verify Stokes' theorem in the last problem. Okay, so last problem. So this is problem 10 in homework 6. Okay, so let's say you have the paraboloid. Paraboloid z equals to 9 minus x squared minus y squared with the z positive or 0. Okay, and so we fix orientation on this paraboloid. Let's say the paraboloid, so we orient S with an upward pointing normal vector. Okay, so orient S with upward pointing normal vector. Okay, so in other words, so this paraboloid is just x, y, and z. So z is positive or 0. So which means that, so if z is positive, it means that 9 minus x squared minus y squared is positive. So in other words, x squared plus y squared is less than 9, right? Anyway, so the vertex of this paraboloid, or the highest point is this paraboloid, is when x and y both are 0. So then z would be 9, right? So this is like have here, let's say 9, and so then you get your paraboloid. Okay, so this is supposed to be 9 here. This circle on the xy plane, this is the circle, that's when z is 0. So that's x squared plus y squared equals to 9, right? And anyway, so we need to orient S with upward pointing. So it's upward, so which means upward, orientation, right? Okay. Now, what will be the boundary of this paraboloid? Well, first, let me just give you the vector field. What's the boundary of this paraboloid? Well, the boundary is just so this is my surface S. Here's my surface S, and so the boundary would be just this is the circle. So here's my boundary. So that's my curve C, which is the boundary of the surface S. All right. So the boundary is just the circle which lies on the xy plane. It's the circle x squared plus y squared equals to 9, right? So we just write it for you here, guys. So the boundary here of S, it's just x squared plus y squared equals to 9 with z equals to 0. Okay, that's the boundary of my paraboloid. Does it make sense why the circle in the bottom on is the boundary, right? All right, so
no, actually no.
No. It's the boundary of the surface because your surface is this thing here. Here's your surface, right? This is supposed to be a surface. All right, so we have this. I don't see if do you see my hand?
Yes.
Okay, so you see there's this paraboloid here in the top, and then oops. Okay, so here's the paraboloid in the top, and so the boundary is just the circle here in the bottom, because this is my surface, right? This is my paraboloid, right? So here's the boundary is just the.
Oh yeah, okay.
Yeah, just a thing in the bottom. And yes, so your vector field F, let's say F. So my vector field F of x, y, z, let's say is equal to 2z minus y x plus z and 3x minus 2y. Okay, and we're gonna verify. So we're gonna verify Stokes theorem. So first step. So first thing we're gonna do, guys, we're gonna compute this double integral of the curl of f. Okay, so first, so I'm gonna compute the left. sorry, the the left side of my formula, right? So first we're gonna start with so step one, we're gonna evaluate this double integral of the curl of f along the surface S. All right. So first, I need to compute. I need to compute the my normal vector. I need to compute the curl of my f. I'm gonna probably just give you the answer, guys. So for example, for the curl of f, I mean this is f. So the curl, I mean, okay, I'm gonna just probably write down here. This is just here you have I, J, K cross product. This is delta X, delta Y. I think we use the curve to see to check if the vector field is conservative, right? So you know how to compute this this curl of f, I guess. Well, at least it was in homework number 5. Right. So here you have like the components of f, like 2z minus y. Here you have like x plus z. Here you have like the x minus 2y. Sorry. Anyway, so you have to compute this this cross product, and it's not that bad here because you see it's just derivative are just constant, like derivative with respect to y here. That will be -2 minus derivative with respect to z of x plus z. That's 1, so it's like -2 minus 1. This is just a -2 minus 1, and then I think it's going to be 2 minus 3, and then 1 minus -1. Anyway, if you have trouble with the curl, just let me know. So here, this curl of f is just this vector field, -3, -1, 2, which is of course not 0. Anyway, now we have to compute the normal vector. Okay, so now normal vector, the orientation of a normal vector. Oops, sorry. So normal vector. So that will be, TU. I think TU is just oh, we didn't parameterize S, right? I forgot to parameterize S. Did we? No, we didn't. Okay, we didn't parameterize S, so we need to parameterize S. S here is very simple because it's just the graph of some function. So guys, so the S here, S is the graph of, because you have z is equal to 9 minus x squared minus y squared. So that's the graph of the function. It's like you're saying z, which is f of xy, is equal to 9 minus x squared minus y squared, right? We discussed the graph of the parameterization of graph of functions. So we said in this case, the simplest parameterization would be to say, well, x is u, y is v, and then the third component would be the function f of xy. So in this case, that will be f of uv. So that's u v, and then 9 minus u squared minus v squared. All right. Now, what are the domain here? Domain. We need the z to be positive, right? We need the 9 minus u squared minus v squared to be positive. So we need u squared plus v squared to be less or equal to 9, right? That's the domain. Anyway, so that's my parameterization. It's just a graph, so it's straightforward. And then now we have to find the normal vector and see if it's the orientation is the one required in the problem. So here, so derivative here, it's very simple: 1, 0 minus 2u. Very simple here too. This is 0, 1 minus 2v. Cross product my normal vector and so tu cross tv, that will be equal to, so in this case, is 2u 2v, and positive 1. Okay, now we need to check the orientation here. If it's upward, right? Remember in the problem we said we need the orientation to be, where's the orientation? Yeah, here, upward pointing orientation, right? So we need to pick a point. I would say just pick a random point. I would suggest just to pick the point, the top, like in this case. So we need to check, sorry. So check the orientation here. So we pick a point, So we pick a point. Let's pick the point on the top. The point of the top is just a, when u is 0, v is 0. So phi of 0, 0, that will be the point 0, 0, 9. Right? That's the point in the top, the vertex. Anyway, so what will be the normal vector at that point? At the point 0, 0, 9. So that's u equals to 0, v is equal to 0. So that will be 0, 0, positive 1, right? Again, because here u is 0 and your v is 0. So you get the vector 0, 0, 1. So vector 0, 0, 1, that's exactly what we need, right? That's upward pointing, all right? Like here, this is, where is it? You see here, so this is my point, this is my point 0, 0, 9, right? So if you draw the vector 0, 0, 1, it would be this vector, which is upward pointing. That's perfect, right? That's exactly the orientation we need. Okay. Any question, guys, about this orientation? Nope. Okay, perfect. So this is good. And now we can evaluate our integral. So just to say this is the right orientation. All right. So evaluation of the. So now you can evaluate your double integral of the curl of f. So what's the double integral of the curl of f over this surface S? So double integral here. So curl of f, it's we said it's -3, -1, 2. Scalar product with the normal vector, which is 2u, 2v1, du, dv. All right. So this is again. This is my tu cross tv, and this is my curl of f, right? And this is scalar product. Du dv, the domain, you need, of course, you need u squared plus v squared to be less or equal to 9, all right? Du dv. So, of course, here, because the domain is, it's the interior of a circle, it's better to use, it's better to use polar coordinates in this case. I think you know how to do this, guys. I mean, this is just u squared plus v squared. Let me just write down here very quickly. So it's going to be -6u, like -2v plus 2u plus 2, right? 2 times 1 du dv. So use polar coordinates because the domain is inside of a circle. Polar coordinates, right? So this is just double integral, -6r cosine of theta minus 2r sine of theta plus 2. And don't forget the Jacobian. This is r dr d theta. Okay, don't forget Jacobian. R, so this is r is between 0 and 3, and theta is between 0 and 2 pi. Okay. So this is very straightforward. I think the answer in this case would be 18 pi. Okay, it's not I mean, the integral is very easy to compute, right? And so the answer actually is going to be 18 pi. All right. Now we have to, well, already over time. Well, now we are supposed to, to evaluate the line integral along the boundary of S, right? So now we have to evaluate the line integral of our vector field f along the boundary of S. So let me just say one word very quickly, guys, because the time is over. But let me say what will be the orientation of the boundary in this case. All right. So I'm gonna use my right hand, right? My thumb points the direction of the, it's upward pointing, right? Here's my thumb, right? And then you see the index finger, that's the orientation of the boundary, right? And the middle finger would points inside the you know, inside the curve, the curve, the boundary, right? Inside the boundary. All right. So you see, so then the orientation of the boundary is given by it's supposed to be counterclockwise, right? So it's counterclockwise because the thumb points in the direction of my upward of my normal vector, right? So then the index finger, that would be the orientation of your curve C. Okay. If it was like, if the normal vector was downward pointing, right, then the orientation of your C would be clockwise. Do you see my hand? Anyway, so yeah, so in this case, because it's upward, then the orientation of the curve C would be this one here. Let me just change the color. 1 second, guys. So it's counterclockwise. All right, guys, I'm sorry, again, I'm running over time. I haven't finished the example here. We need to evaluate the second, the line integral of f along the boundary and compare with the double integral of the curve of f. Anyway, so we're gonna continue this next time. Gonna continue this example next time. I'm gonna show you another example to show you why this Stokes theorem is powerful. And then I'm gonna talk about the last theorem, which is Gauss divergence theorem. All right, guys, we're gonna stop here, stop recording, and thank you, everyone. Don't forget,